Hello world, it's Craig. Today we're going to look at RAMless diagnostic software for this Digi-Key SCMP-based NIBBLER board. Of the bare NIBBLER boards that I sent out a while back, 2 of the builders have contacted me because they can't get their board going. Now one of those builders is my buddy George, who sent me his board to look at so I can see what's going on. Now George has built a number of my projects before over the time, and I swap technical emails with him now and again, so I know George is smarter than the average bear when it comes to digital electronics. But George doesn't have any way of testing these components. He doesn't have one of these retro chip tester pros, which can test everything on this board except for the processor. And he could test chips individually by hand, but that's just a waste of time. Now George, I looked at this. He did a good job of building this board. He's double-checked the obvious, like the solder bridges and the like. And George says he's getting a good clock off of this, so I was convinced that there was a dead chip somewhere. Since I knew that George was going to be sending me this board, and since he wasn't the only one that's going to have this problem, I decided to come up with some diagnostic hints and write some RAMless diagnostic utilities for these SCMP processor boards. And this software utility should be fairly useful for anybody that's working on SCMP hardware, not just this Digi-Key NIBBLER board. And this board isn't glitchy, it's dead. And a major problem with the board running Nationals Nibble Basic, yes, I realize that saying Nationals and Basic is doubly redundant, but the problem with running Nibble Basic is that nothing works on this board until everything works on this board. You have to have all of the decoding, the RAM, the serial I/O, everything has to work before you'll see any life out of this nibble at all. And the diagnostic code that I have written for this, it takes care of that for this. And I'm always preaching about the benefits of getting communication with processors and running RAMless diagnostic code as soon as possible. And, that's the prime purpose of this serial port doodad dongle that I talked about some time ago. This lets you hang a serial port onto nearly anything, and then with some good diagnostic software, it breaks the hardware down into little functional subgroups, and to a great extent, often those can be tested individually. But fortunately for this, we won't need this doodad because there's a serial port already on this board that we know about. And getting the board to fetch instructions from the base EEPROM is usually not all that tough, especially if it's a design that's known to work. And then there's just something wrong with a chip or a trace or some other hardware problem. But this is also the first step if I was testing a new design for debugging and I had a problem with it that I couldn't figure out. Back to this one, George said it'd be okay if I did a video on fixing this board, but in this particular case, the diagnostics went a little bit faster than what I was expecting. I took out George's Nibble EEPROMs and I put in the diagnostic code, did a restart, and the board came right up. So since it seemed like his EEPROMs were the issue, I compared the EEPROM contents with what should have been in those for Nibble. And in this high EEPROM, there was a stuck least significant bit in many of the memory cells. So I still wanted to go over the diagnostic software for the SCMP, but I'll do it on my board so I can get George's board back in the mail. I am back with the diagnostic utility in my board. I'm not going to go through the specific code. You can download the source and build files off the SCMP project page. In addition to the source, list, and hex files, there's a little support document that gives waveforms and additional hints on the use of the utility if you have some SCMP project. Now, when I'm writing this sort of diagnostic utility, I divide it into 2 purposes. There's low-level tests, mostly loops meant to be used with a logic probe or oscilloscope to find problems. And on this menu, there's ones marked with an asterisk, and once those are started, they will loop until the system is reset. The idea is that the logic probe is going to be set up so that we can see the address being fetched as well as whatever signals are tied to that debug. And then once I get a logic capture, then I look through the program listing and follow the code and confirm what should be happening is happening, or determine where things are going wrong. Maybe reconfigure the logic probe and try again, maybe tweak the code a little bit, broaden the data being captured, or focus in on a particular curiosity. The other tests down here are higher level. In this example, most are useful for issues with memory. Sometimes the focus is I/O or some other peripheral, but in these tests, they're mostly to give information about the onboard memory, and it gives the results back to the terminal. Now, all tests can be initiated with this command prompt, but it's really useful when at least the most fundamental low-level tests can be automatically started when the system is reset. And that eliminates one more point of failure, which is communication with the terminal. Now, I did a video earlier talking about this serial port dongle doodad, where I start with diagnostic software that tells me what delay values to use for the serial delay, and then little by little it builds on itself until communication is established. And I use that a lot for boards where I know absolutely nothing about the board. But here, we have the schematic. We know what the delay values need to be for the serial communication. We know where the I/O pins are located and so forth. We're just bit banging out a serial port. And the point being that what I'm showing in this video is a mid-level diagnostic utility. Sometimes I need to go more towards the fundamental and sometimes more towards the overall system operation. And sometimes I need to bring in other hardware tools like the serial port dongle doodad. So back to this test. As I was saying, it's useful if the most fundamental load tests can be started automatically when reset. And fortunately, the SCMP gives us 3 digital inputs that can be used as configuration flags on reset. So for this utility, I use the serial in and the sense A to determine if any of these loops should be started automatically when the board is reset. So with these 2 inputs, I picked the 3 most fundamental tests, and any of those 3 can be initiated by tying either the serial input pin or the sense A to either ground or 5 volts and then resetting the processor. When the program starts, it looks at those 2 inputs to determine if one of the low-level loops should start. Now, these 2 inputs, they don't tend to float high or low when they're not connected. They're pretty indeterminate. If they're left disconnected, who knows what loop will be initiated. Sometimes it'll come up in one loop, sometimes it'll come up in something else. So when you're doing this, you need to make sure that you have both of those tied to what you want them to be tied to. And right now, I have both the serial in and the sense A tied to ground, so that after a reset, the utility skips those tests and it continues into the command prompt, which is where we see it now. If we look at these tests, the most basic test is the instruction fetch command. And it's by far the simplest test since it's just a one-line infinite loop that just jumps back to itself. Of course, if the processor can't fetch an instruction, then we can't even get to this test. But nonetheless, it's a good test to make sure the processor is not being interrupted, that it's consistently fetching correct data, and so forth. Plus, it can just be a starting point for some modified test if you want to look at something else in more detail. Now, all these tests are in order of sophistication and not alphabetical, and the next is the digital input test. It simply reads the 3 digital input pins, serial input, sense A and sense B, and displays their status to the terminal. And we're stuck in this loop until we do a reset. Flag sequence count is the next one, and the loop continuously sequences the 3 flag output pins from 000 to 111, and then it just rolls over. So those are the 3 tests that can be triggered just by configuring the serial in and the sense A before a reset. The next test we have is the write and read back test. The user can select an address in hex, and then the test will write a value to that address and then read back the value from that location. The readback value is displayed on the console, it's incremented, and then it's used in the next write. For a lot of these tests, as you can see here, I backspace or use the carriage return without a line feed to just overwrite the old values. However, if you want to see them scroll by on TeraTerm, the new line can be changed from a carriage return to auto, and then we'll see that it'll show these individual values on one per line. So if you need to go back and look and make sure that something is not missing, then that's a good way to do it. The final low-level loop is the address decoder test. During this test, it does a memory read from the first address of each 1K memory block. So it reads from 0 and then 400, 800, C00, and so forth. Since memory decoding is a critical aspect of any of these boards, it gives a chance to strap on a logic probe and make sure that the memory is being selected as desired, and that memory read and write strobes have the proper timing and so forth. Now, since the SCMP multiplexes the high address nibble and perhaps any hardware or design problems is in the address latching, this test also outputs the high address nibble on the 4 output pins, 3 on the flags, and the last one on the serial output. That way, when doing diagnostics, the user can jumper or bypass parts of the decoder logic that they're testing. So these low-level tests should at least help solve any hardware issues with bad chips or design bugs. And once the board can fetch an instruction properly, and if the sense B input and the flag 0 output work, then the board should be able to get to the command prompt and the test can be selected through this menu. The rest of the tests are higher level. Generally, they're less reliant on logic analyzer, and they'll return back to this command menu when they've completed. And they're all diagnostic tests for memory, but they're most useful on RAM. The map RAM test searches the entire memory space and displays any contiguous blocks of RAM that it finds. It doesn't know the difference between a primary RAM address and any overlaid memory blocks. The map RAM test will not consider an address to be valid RAM unless the full byte is stored and correctly retrieved. However, on these boards that use 1 byte wide or nibble wide RAM chips, maybe the board is working, but there's one or more bad RAM chips, and in those cases, the sticky bit test can be useful. Sticky bit also does a scan of the entire memory space, but it's for partial bytes, and it'll report back any address that has any sticky bit between the write and the read. Now this test isn't perfect because it will pick up some addresses that just happen to be susceptible to outside influence. The sticky bit test isn't very thorough. It reads the byte, it complements it, it writes it back, and then it reads it again. And any bit that can be saved and recalled correctly is considered sticky. And it has its quirks, but it can be a useful tool. And when sticky bit finds an address that has a sticky bit, it prints out the comparison. And so this is the space in the upper ROM, which is actually empty, but we're getting back the occasional bit that can be influenced. Now when we're up into the actual RAM, we can see the sticky bits are all 0, meaning that there were no errors in those sticky bits. Now the RAM test is quite a bit more robust. This starts at a user-specified address, and it scans up from there while performing a more thorough memory test. It writes and reads 4 different values to each address, and with each value, it writes something else to the adjacent RAM addresses. And then for each address, it prints out if that bit matched all tests or if it failed in any way. So here we're seeing equal signs. That means that it was equal for all those tests. And like the other higher level tests, this one will return to the command prompt when it gets to the top of memory, or you can just reset the board. And then finally, we have the version command. And it seems trivial, but I find version numbers to be very useful, especially in this kind of software where I'm always tweaking it for exactly what I need to do at the moment. Now, I think the primary directive in writing this early level diagnostic software is that it needs to be entirely RAMless. The goal is to eliminate anything that can go wrong, and RAM is a big unknown when resurrecting any system. Now, without RAM, the code is limited to whatever registers or stack pointers built into the processor, but don't forget there's other places where you can hide a nibble or a bit just short term. And often I find myself pulling stunts that would normally get people fired as bad coding practices. So for example, put C, which we worked on earlier, it's called by many of the tests, and most of them do not have any registers to spare. And knowing that this diagnostic is always going to be run in the base ROM socket, the high address nibble always will need to be 0 when I return. So I use that high nibble in the put C routine as the bit counter, and then I just set it to 0 for the return because I know it has to be 0 because that ROM is in the low address spot. So if anyone has a SCAMP project on their bench at the moment, it would really be useful to get some feedback and see if this utility is helpful to whatever hardware they're running it on, because I've only been running it on this little nibbler. And also, let me know what works and what's missing. Okay, now let's look at this hardware. This board, it's been working fine, but if I had a board that isn't working, and if I have the ability to test the chips, which I do with my little Retro Chip Tester Pro, then my preference is usually to pull the chips out, test them, put them back in the board to continue with the diagnostics. But if I can't test the chips, or if it's a big board that just has more chips than I want to test, then I really don't think I have a preferred method. Sometimes I'll just start digging until I find bad chips or whatever the next problem may be. And sometimes, especially on really simple boards, I will work my way down and simplify the board to what I see as minimum system and then start the diagnostics from there. The reason being that sometimes a bad chip can spoil the fun for everyone else. For example, this is the little 2102 RAM that has an output that does not properly tri-state. And so even when that output should be disabled, it pulls the data output line high, and that pulls it high on the whole board and causes not only a little bit of contention, but it causes the whole board to fail. And I found this chip was bad by testing it. But if I were debugging the board, I think it would have been an easier chore to get the board working without the bad chip and then see if the board fails when I gradually start to repopulate the board. One bad chip like this is the sort of problem that the sticky bit test is useful for. So as I've mentioned a couple of times, this Retro Chip Tester Pro can test everything on this board except for the CPU. But let's presume we don't have that. So if this board is dead, then all of these chips are suspect. The S in SCMP stands for simple. So let's take a look at this little Digi-Key NIBBLER board and see just how much we can simplify the board if it isn't working for some reason. And the question is, how many of these chips on this board do you think we can remove and still have a fully functional board? If you looked at the thumbnail, you already know the answer, but if you didn't, I suspect that we can remove more chips than you would have originally guessed. So first of all, I don't need any RAM. And if there were any others that were not tri-state in their bus or loading the input down, then they could stop this whole board from working. So if I were diagnosing this board, I think one of the first things I would do would be to take out the RAM. So let me power down, take that RAM out. Okay, now all the RAM is out. Let's power this back up and make sure we get our command prompt. Yep, we get our command prompt. Now we could do a sticky bit test, or we could do a map RAM or a test RAM. Test RAM 1, 2, 3, 4. We can see it fails all of them because they're just not there. Let's look at these 381 LS97s. There's U7, U9, and U4. Now these are tri-state bus drivers, but they're always enabled, so here they're just being used as buffers. Their only purpose is to boost the drive capability of the processor for the large fan-out required by the 16 RAM chips, the 2 PROMs, all the glue logic, and whatever's on the bus. Now this top one, U7, drives the output data. The middle one does the low address byte, and this bottom one does the high address nibble and the bus control signals. Now there's next to nothing loading down the bus, so it doesn't need a lot of drive capability. So I'm going to bypass these two on the address and the strobes, U4 and U9. Now because the address needs to be passed through to the rest of the board, I'm going to replace them with these little pass-through sockets that I've made. Here I've just used old resistor leads from the discard pile and I stick them into a socket. Then I leave little loops so that I can put them on a probe, a logic probe if I need to. And then sometimes I'll solder them in so that they don't fall out when I'm not looking, but these are all pretty secure. So these are just shorting the input pin to the output pin. And I use these sockets so that I don't damage the sockets that are already on the board. So let me power off and take those guys out and put in these little jumpers. Power back up, we still get our prompt. Now let's look at this address decoder U2. Now its purpose is to break the memory space down into 1K blocks and then enable whichever chip is located at that block. Now if either of these bottom two 1K blocks are selected, then this AND gate enables the lower EEPROM. And then the other AND gate above that decoder selects the upper EEPROM if either of the next two blocks are selected. In page 1, the two RAM banks are enabled directly because they're each 1K themselves. And then finally, these extra two 1K blocks are taken care of off board for somebody else to use. But we don't need any of this. If we take out the upper EEPROM, that only leaves one memory device left, and that's the lower EEPROM where the diagnostic program resides. I'm going to pull out this AND gate, U1, and run a patch wire directly from the ROM's asserted low chip select to ground. And that means this lower EEPROM will always be selected. But the outputs will only be enabled when the enable signal is asserted, so everything should still be okay. But before I do that, let's look and see if I can take that AND out altogether, or if I'm just going to need to lift up that one output pin and put it back in for something else. Now that AND is used for the reset and the clock, and we can live without either of those. So I'm just going to jumper across the reset input. And the reset won't be as clean without this AND gate, and we may get false starts as it bounces, but I think we'll be okay. So let me power off, take out this AND gate, and then I need to jumper the chip enabled to ground. And I think the way I'm actually going to do that is I'm going to take pin 8 down to pin 7, and that'll enable that chip select. So let me just put a little jump wire in there from pin 8 to pin 7. Okay, that enables the chip select on the low ROM. And now I need to jumper across from pin 1 to pin 3 for the reset. Okay, so now I've got pin 1 to pin 3 for the reset, and pin 8, which is the chip select for that ROM, taken to pin 7, which is ground. Okay, so let me power up again. Make sure we've still got our prompt. Yep, everything still looks good. Now I left this decoder U2 hanging, but it isn't doing anything because we hard-tied that chip enable to ground so this whole U2 can come out. Okay, now let's look at the 74-174 latch. The SEMP has a multiplex address bus like the 8085, but where the 8085 multiplexes the whole address byte, the SEMP only multiplexes the high address nibble, addresses 12 through 15, and those are captured in this latch. But we've taken out that decoder, and we're not using those addresses off board, so nothing else is using that latched address. So we can go ahead and take out U6, this 74LS174. So let me power off and take that guy out. Okay, power back up. Still got our prompt. Now I took out the RAM, so there's nothing left that needs to write data. So just like the latch, this buffer U7 isn't doing anything. And in fact, he's so not doing anything, we don't need to jumper him. We can just take him out. So I'm going to take out U7, confirm that we still have a prompt afterwards. Okay, that guy out. Yep, still got a prompt. Okay, let's look at this inverter. That inverter was making sure that that clock strobe on the latch was the right polarity. But without the latch U6, we don't need that inverter on the clock strobe. And other than that, the inverter is only used to buffer between the processor and the real world on the serial port. The received data is double buffered, so I'm going to take out that inverter chip and run a jumper so that the received data goes directly into the sense B. So I'm going to take that out. That's from pin 11 to pin 8. 8, 9, 10, 11. Okay, so that jumper's in. Now the transmit data is a little bit tougher because it only goes through one inverter. So that's why everything we received when we were working on the Gecko routine and such that we had the transmitted bits inverted when we sent them. So without that inverter, the terminal won't understand the serial port. But in the diagnostic software, I output the transmit bit to flag 0 like normal, but then I invert it and output that onto bit 1, or flag 1. So now that I've taken out that inverter, all I need to do is switch over and connect the transmit data to flag 1 rather than flag 0. So that means I'm going to go from this inverter, pin 4, over to pin 1, which is flag 1. Okay, so let me do that. Now just to check, let me power up. And I still got our command prompt. That's good. So our board's starting to look pretty bare. And finally, there's U8. Now, U8 is another one of these LS97 tri-stated bus drivers. Now, its purpose is to drive the data bus onto the processor's data lines during a read. So that incoming data, either from the onboard memory or this edge connector bus, goes through that buffer and onto the SCMP's data bus when the read strobe is asserted. So anytime other than a read cycle, U8 is disabled because either the data bus is idle or the processor is driving the bus. But now, since there's only one external device putting data onto the bus, and that's our EEPROM, and it has its own output enable, U8 is actually redundant because these are both turning on at the same time. So it can come out, and I can put a shorting socket in that to pass the signals through when the EEPROM is enabled. So let me take the power off, take this guy out, and put another shorting block in. All right, finally let me power up, and I still get the command prompt. So now this EEPROM's chip select is always asserted because we have that jumpered over here on this AND gate. But its outputs are only enabled when the processor reads strobe, because we're passing the read strobe through one of these buffers over here. So only when the SCAMP does a read is this guy get enabled. So we can see the beauty of this SCMP and this NIBBLER board. Right now, this is a completely functional system. The software is running. Board's up and running with just a processor and an EEPROM. There's no glue, there's no RAM, there's nothing else on this board. So now we can get in and do some good old-fashioned low-level diagnostics. At this point, armed with these low-level tests and the diagnostics, I think it's quite straightforward to find any hardware problems, like solder bridges or a wrong component being installed. And then when the board is working, once we can get the command prompt, which we already have over here, then we can insert a chip or two, run through the diagnostic tests again, and if there's a bad chip, it'll be discovered soon enough. So we can get this board, we can test every chip, even if we don't have something like this Retro Chip Tester Pro. I think this is a good stopping point for this video. I actually wasn't going to do any of this, including making the diagnostic utility, but when 2 of the 4 people that I gave boards to had problems, I think it was worth taking this little detour. Because I'm sure there's many dead 81 LS97s that are being hawked on eBay, as well as dead INS 8060s, 2102 RAMs, anything is suspect on this board. And as it turns out, of the 2 people that had dead boards, both of them, it turns out that it was a problem with the EEPROMs. Actually, I take that back. Ray also had a dead chip. They're a dead processor. So hopefully these hints and this RAMless software utility can help sort out any problems. So, you certainly don't need a chip tester, and maybe you can get by without even a logic probe. As always, this channel is not monetized and entirely fueled by likes, viewer engagement, and sharing. Thanks for watching. Talk with you later. Bye-bye.